So also in the next slide, okay, now then this is this right-hand side, right? This right-hand side when we derive power expression using the formula for this periodic signal, okay, for this periodic signal. So this right-hand side again. So now because of this the variable of the integral in this case t, so that's why this after integral the result actually is a signal. But again, the signal is in this case the variable is now becomes tau. It's okay because tau or t is whatever the variable, but they are all indicates time. Okay, so this is why now the right hand side, the definition is also is a signal, it's a continuous time signal, and then so because now we know that this ST signal, right? This ST signal actually is a periodic signal. So this is why we can use the Fourier series, right? The Fourier series representation of a periodic signal, and we can replace each of these terms with its corresponding the Fourier series representation. Okay? And as I said, because I skipped to obtain this final result, okay, we skipped a lot of intermediate procedures. Okay? And some of the students actually are quite interested in how we can actually all those intermediate procedures to obtain the final result. Okay, and I have also done. Let me see. Okay, yeah. So this is the intermediate result. Okay, intermediate result. That means to show from this reference to show this equivalence. Okay, this is what we want to show here, and then we can go to all you just this is the Fourier series representation of this given periodic signal ST, right? And then through a few intermediate procedures, and then we can also derive what is the complex conjugate of the Fourier series representation of the complex conjugate of this given signal ST, also shifted by tau. In particular, I also write it here because this particular ST plus tau, the conjugate complex conjugate ST, is actually equivalent to ST times the complex conjugate of the ST minus tau. But this is simply, you can show that because you simply do a change of variable. And then, so to obtain the Fourier series representation of the complex conjugate of this, the time shifted version of this ST, and then you obtain in this form. And then when you group these two terms together, when you rearrange all these complex exponential terms, and the key idea is you can see that this particular term is actually when m equals to n, and this is 1. Okay? And then the integral is simply 1, because t0 divided by t. Okay? And then if for all other cases of m which is not equals to n, and then we know that because this is a complex exponential, which is the the sinusoidal signal, right? So the sinusoidal signal, if you integrate the sinusoidal signal over the integer multiple of the cycles, right? And then the area simply is 0. So positive, negative cancel each other. So this is why for all other m value which is not equal to n, this is 0. So that's why finally we can simply obtain that these closings and this term is simply 1. And also for m equals to n. Right? So this actually you remove this this information because only when m equals to n, okay, and this term the value is 1. For all other m value it is 0. Okay? So finally, we see that now you have this Sn times the conjugate, right? Complex conjugate of Sn. But we know that m has to be n, and this is why we have this square of the magnitude of Sn. This is here. Okay? Yeah. Okay. As I said, this is the intermediate procedures. Again, this is not required. So for those students who are interested, I have made a copy, and then you can get a copy from me, okay? If you're interested in this one. But yeah, as I said, this is not required. We only need to for this purpose of this course, you only need required to know this result. That means the power spectrum of periodic signals is actually you simply just take a Fourier transform of this particular term. And this is what the result here, because I take the Fourier transform of this one, and then it's simply a linear combination of the impulse function. And the coefficient is simply now the square of this magnitude of Sm. Okay. Yeah, so we actually have tutorial problems to utilize this formula to derive the power spectrum of a particular periodic signal. So we will for those that did not attend yesterday's tutorial, we will discuss the questions shortly after this lecture. Okay, so now let me continue the last week's lecture because where we left off. Okay, last time we finished talking about this bandwidth. So basically, this is the definition of the signal bandwidth in this course. Is the bandwidth of the signal is the amount of the positive spectrum, and then the effective bandwidth is the percentage of the signal's power or energy included, okay, based on the requirement. If you require 90% of the signal, and then you find out what is the range of the bandwidth which 90% of the power or energy are included. So this is the definition of the bandwidth and also the effective bandwidth in this course. And then, okay, finally, this topic is for the again. So this is something we have learned in the signal system. Is that when we transmit a signal through a linear system. For example, in our case, if you model a channel, if we model a channel as a linear system, okay? And so we can use the theory of the linear system which we have learned in the signal systems, and it's now that the analysis of such although an ideal and simplified model, but it's actually useful because the analysis becomes relatively easier, okay, when you're dealing with a linear system. So in particular, we know that in the linear system, so the linear system, which is in the time domain, if a system is a linear, and then it's a response to the so-called impulse, unit impulse signal, delta t, is defined as the impulse response. And then we know that from the theory of the linear system is that the characteristics of a linear system is completely described by its unit impulse, its impulse response. Okay? And in particular, we also have this also the property called the time invariance property, right? And what it says is that if you obtain any signal, any input signal, if you shift the signal, right, by a amount of, let's say, for example, tau. Right? So remember for the linear system, so if you have an input SD, right, through a channel, this is linear channel, okay, and let's say the output is YT. So what is if let's say now we have LTI system, which is a short form for the so-called linear time invariant system, and so what it says is now if you shift the signal st by some amount tau, right? And then the output also is simply the time shift devotion of this the yt by exactly the same amount. So this is time invariance property. So we know that if the system has both the linearity property and also the time invariance property, so this is what we call a linear time invariant system. And then now we have a interesting result is that the output, let's say for the arbitrary signal input to a channel. Let's say if this channel is it's a linear time invariant system, okay? And let's say the impulse response of this system is ht notation, and then we know that because this is a linear time invariant system, and then the output of the system is the response of the system to this input signal st is simply as a it's a convolution. So basically, you just take a convolution integral of these two signals, and remember this star operation here means the convolution operation. So it is equivalent to take the convolution integral of this form, the two signals. One is the input signal st, and one is the channel impulse response st. And then, so we know that this Fourier transform property, one of the important Fourier transform property is still called the convolution property. Which says is that if now we have two signals, st and ht, okay, you need to do a convolution operation in the time domain, right? And then if you take the Fourier transform of this signal, okay, and this is actually equivalent simply in the frequency domain, the result, right, is the spectrum of this yt, right, is simply a multiplication of the corresponding spectrum for the transform. So this is a convolution property of the for the transform. And because of this nice property, now it makes, right, if let's say we model the channel as a linear time invariant system. And then it turns out that the analysis of this the channel response of arbitrary input signal becomes much easier because everything can be done now in the frequency domain, and we also need to deal with the multiplication operation rather than doing everything we need to solve integral in the channel. So in the signals and systems, the bit of the terminology. So for those students have taken the signal system, and so this the Fourier transform of this impulse response is what we call the frequency response. And then the transfer function is only the term we use for when we are dealing with this everything now in the here somehow in the literature of the communication systems, they actually call the frequency response also as so yeah, we will just be consistent now with the terminology used by the literature of the communication system. Okay? So the students have taken the signal system. So this is equivalent to as the so-called frequency response. Okay. Now let's have a look at a few two ideal the ideal the LTI system. Okay. So one is so-called the ideal low-pass system, and this ideal low-pass system, the transfer function or the frequency response of the of the system is in such a very nice form. Right? This means that for all the frequency outside of this, within this range from minus BH to BH, okay, and then the this magnitude, okay, magnitude is 1. Okay. That means you so like you can treat it as you have a gain. Okay, you have a gain. Okay, so within this frequency range, okay, and the gain of this ideal low pass system is 1. Okay, and outside of this range, right, is 0 by definition. This is so-called ideal low pass system. Okay, and so what it means is now if let's say you have a signal, input signal st, okay, and let's say this is the spectrum of this signal st, spectrum of this signal st, okay, which indicates all the frequency, the components which is included in this signal. Right? So you see that now if we pass this signal, right, if you carry this signal through linear time running system, also here is an ideal low pass system, right? So we know that, okay, of course, because of the property, motion property, Fourier transform. So now in the first domain, right, the response, right, the frequency response of the response of this this ideal low pass system to the input signal, also in the first domain, right, is simply a multiplication between this spectrum and also the spectrum of this ideal low pass system. And because of the characteristics of this ideal low pass system, you see that within this bandwidth range of the frequency, everything is passed. You simply multiply by 1, everything is passed. Outside of this range, right, is just cut off. Everything is gone. Okay. So this is also what we mean is cut off. It means the pH is so-called cutoff frequency. Within this, less than this one, pass. Beyond this one, pass. Okay. All right. So you see that now, if let's say we have an ideal low pass system, so the condition is that if now we have this pH, right, the value of this pH is larger or equal, so long as it is larger or equal to this pH, right, and then the result is that all the spectrum of this signal can be effectively passed. This is the characteristic of this ideal low pass system. So this is what we call a low pass. You pass the frequency from 0 up to some Bs. So this is called low pass. And also we have a so-called ideal band pass system. And the ideal band pass system now this transfer function of frequency response of this system is defined in this form. So you see that now in this case this pass band, right, the band which we pass is actually centered at a frequency fc, okay? And then also cover a complete range of the frequency, which of bandwidth pH. So now if we have such an ideal band pass system, again now if we have so-called baseband input signal, or the baseband input signal is that the bandwidth of this input signal is from 0 up to Bs, including all these frequency components from 0 to Bs. So again, if let's say this bandwidth input signal, the bandwidth is Bs. Okay? So now if we somehow we just shift, if we shift this spectrum to also now center at this Fc. Okay? And again, so the bandwidth is Bs. Okay? But in this case, now because we shift to this Fc, so the total now the bandwidth is from is minus Bs to Bs is cover 2 Bs. Okay? You apply 2 Bs, 2 times the Bs bandwidth. And then again, so if we have this ideal band pass system, okay? So that means now this if this signal somehow we shift it spectrum to this center at the Fc, so we pass this you carry by this type of the channel which is represented as the ideal band pass system, right? And again, because now you see that if let's say the pH is larger or equal to 2 Bs, right? So if the dH is larger or equals to 2 ds in this case, and then again, so all the spectrum represented by this particular signal can be also effectively passed. Okay, so this is true. The ideal the system which will be used in this course to model in the particular channel. So this is what we call in particular this low pass system, the ideal low pass system. We'll use it to model so-called the baseband channel. The baseband channel. So what it means is that the baseband channel will efficiently pass the frequency components from the zero, also the DC, the direct columns, DC, and to the cutoff frequency DH. So this is because of the characteristic of the ideal low pass system. And on the other hand, we also have the so-called band pass channel, which is modeled as the ideal band pass system. Is that this channel will efficiently pass all the frequency components within a certain band between this fc minus half of the dH and fc plus half. So these are the two type of channels which we will use in this course to model a channel. And typically, you will see that these are examples. Baseband channel is a rational table, and this the band pass channel is the electromagnetic wave, and also as we said, because this frequency of the electromagnetic wave and also the fiber is very, very large. So that's why the regulation will divide all these bands into these various bands of the frequency. This is why we need to this band pass channel. Okay, so this is the basic concepts of the baseband channel and band pass channels. We will just discuss this here, and it will be useful in this course. Okay, so now let's any question? Now let's just move on to this. Okay, so let's just move on to this now the lecture 3. So lecture 3. Now we will discuss lecture 3 and lecture 4. In the next session, we'll also discuss the so-called analog communication. In particular, in this part, is we use the amplitude, so-called amplitude modulation, and next part is the frequency modulation, FM, right? And yeah, so here's a slide which shows that we all should be familiar with the radio, the radio broadcasting in the analog, because in old days, and also actually nowadays still in many parts of the world, we still use the radio. The broadcasting is actually implemented in analog communication system. Everything is actually the analog system. So in particular, we are familiar with this so-called AM radio and FM radio, which effectively actually is involving modulation scheme. AM is for the amplitude modulation, and the FM is for the frequency modulation. And these are the two modulations, the schemes which we will learn with the basic principles. Okay. And yeah, so again, this picture just shows you the the basic ideas how we actually transmit, right? For example, the source is some original sound signal. Okay? So through some, the manipulation basically is handled by this transmitter. Okay? And this transmitter typically involve this modulation. Okay? And then by modulate this, you have this the modulated signal, and then you transmit. In this case, in the case of radio, of course, we just transmit through the free space. In the free space. And then at the receiver side, of course, again, you have this antenna, right? And which attached to the radio, and this is for receiving the signal. And of course, because the received signal is in a modulated form, you need to perform some demodulation to how the signal, so that the signal is as close as possible to the original signal. So this is the basic elements of typical communication system. In this case, it's the analog communication system. So we'll see that the signals are modulated by, they can be based on different schemes. We'll learn in this course, AM. And then, yeah, so in this case, because we're dealing with analog communication system, so the source signal, all the signals in between, they are all analog signals. In particular, this source signal is a baseband signal. And then the channel, in this case, we were dealing with a bandpass channel. Because we need to modulate the signal, shift the signal to some the frequency, FC. This is called the bandpass channel. Okay, so now we will discuss the analog modulation schemes. And there are different methods of the analog modulation schemes. So we will just go through them one by one. So this course and also this this lecture and also the next lecture will be dealing with this part. So yeah, as we discussed just now, the basic idea of this the analog communication is that if we have a baseband signal, right? And this is the spectrum, so we shift this spectrum to some center frequency MC, and then that the channel, if let's say the channel is a bandpass channel, in our case, we model it as an ideal bandpass channel, and then this spectrum of the signal will be passed by this channel, ideal bandpass channel, and then at the output side, at the receiver side, we can obtain exactly the same spectrum of the signal. This is in the ideal case for the reliable communications. So that's easy. In order for all the frequency components, right, of this baseband signal to be passed through this channel, right? It requires that these frequency components of this transmit signal, right? Because this bandpass channel, the center frequency is SC. So first thing is we need to make sure that the frequency components of the transmitted signal, which is in our case is the modulated signal, we shift especially to this band which is centered at this frequency. This is first requirement. You need to shift the frequency component of the original baseband signal to center at FC. And the second requirement, of course, right, is that this bandwidth of this channel must be larger, at least equal to the required bandwidth of the transmitted signal. So this is the original signal. The bandwidth is Bs. Okay. So let's say if the denote after modulation, the bandwidth of the transmitted signal is Bm. And then so what it says is now in this case the Bm must be smaller or equal to this channel bandwidth Bh. So yeah, as we discussed in the last the week's lecture, because the basic idea of the analog modulation can be actually seen from the so-called modulation property of the Fourier transform, right? Is that if we have two signals simply multiply with each other, so in particular in our case now, we will call this is the original signal ST. Okay? So now let's say if the the impulse response of the channel, in this case we are dealing with the modulation. So so this actually is I need to mention here. Okay. Now you see that because for the communication system, right, we need to go through from the source to the user. We need to go through a series of components. Okay. In addition to the channel, we also have this transmitter. We also have this receiver. As we said, in particular, this transmitter typically involves the modulation, dealing with the modulation distance, and then this receiver dealing with the demodulation distance. So each of these components, right, each of these three components is actually can be regarded as a system. Not only this channel, but each of these components, transmitter and receiver, also can be regarded as a system. Okay, as a system. So this is why, if you treat this signal cosine 2 pi ft, right, as the unit impulse response of the transmitter component, remember we need to first do a modulation since. So this is effectively a signal, the signal which we will modulate. So for the in our case, this is modulation. So this is the signal, original signal, and then this is the carrier signal, cosine 2 pi. And in the terminology of the communication system, we call this signal actually is to modulate. This is the modulation signal. To modulate this carrier signal. And then the result of the multiplication between these two signals is what we call the modulated signal. So you see that because of the modulation property of the Fourier transform, so the multiplication between these two effectively is continuous time signal so if we have two signals, S1T and S2T, multiply, right? And then the corresponding Fourier transform is in Fourier domain is simply a convolution between the two spectrum corresponding spectrum. This is the convolution property. The modulation property of the Fourier transform. So you see that again, because we have this derived in last week's lecture, you see that for the for these two signals, if we multiply with each other, so the corresponding spectrum, the Fourier transform of this modulated signal is simply of this form. And then this means that if you plot this whole thing in the Fourier domain, this means that given the original the spectrum of the original signal SF, so the effect is that now we shift this spectrum, create another copy, and then shift the spectrum one to the FC and one to the minus FC. And then the amplitude, right? The amplitude, the magnitude of this spectrum is scaled by a half. So this actually indicates a typical scheme for the amplitude modulating. That means that because by multiply this, this original signal ST, or the ST modulating this carrier signal cosine 2 pi FCT, so you see that the received after the modulation this signal is effectively AST cosine 2 pi FCT. And you see that because this is the amplitude of this signal, and then because this amplitude contains this original signal ST. This is why we call the amplitude modulation scheme. That means the original signal ST in this case is impressed on the amplitude of this modulated signal. So we will shortly learn that this is actually the basic the form of the amplitude modulation scheme. And of course, there are other means of modulating. In particular, you see that this phase modulation is that you impress this original signal ST in the phase component of the modulated signal. And then likewise, the frequency, so-called frequency modulation is that you impress this original signal ST. Now, in this case, on the frequency of this modulated signal. And in particular, this modulation scheme we will discuss in the next lecture. But in this lecture, we will deal with the analog modulation. Okay, let me finish this slide, and then we will have a 10 minutes break. Okay. Okay. So, and for the analog modulation, we also defined a particular performance metric. It's called bandwidth efficiency. We discussed in the first week lecture. And bandwidth efficiency is an important performance metric for communication system. So, which is defined in our case, in this case, in the analog modulation, is defined as we use this gamma notation, gamma, and it's defined as the information. The numerator is the information signal bandwidth. It is the bandwidth of the original signal, before the modulation. And then the denominator is the required channel bandwidth. That means this is the bandwidth required by this channel to effectively transmit the signal through the channel. Ideally, without any distortion. And then, of course, because this required channel bandwidth signal, so it only requires be at least larger or equal to the modulated signal bandwidth. So in our case, in this case, let's treat it as that the required channel bandwidth pH is exactly equivalent to the modulated signal bandwidth. So this one, and then in this case, the bandwidth efficiency is simply defined by the signal bandwidth, the information signal bandwidth, the original signal bandwidth, yes, and divided by the bandwidth of the modulated signal. And of course, from this definition of the bandwidth efficiency, we see that a higher value of this gamma indicates a better spectral utilization, which means we utilize the bandwidth of the channel more efficiently. Okay, so now let's have a break, and then after that we will now discuss 4 different amplitude modulation methods which have been developed in the definition.
夜晚要上咩喎？8、4公隔夜4喎，上咪唔上，冇所謂啫。條得聽今晚隔夜04喎，係啊，所謂點到8點咯。呢啲嘢上 想上
send 翻個 email 俾佢話，唔舒服。
爆四哥就真係扮唔到啦，我扮唔到，我病完你。爆四哥肯定有
13E啦，13蚊。
我即刻去跑下步，即刻除晒衫出去圍住先。
唔係啊，後腦痛都可以攞價㗎。
周神你攞怪嘅，
後痛都可以攞價㗎而家。
咁好嘅咩？
呢陣要上咩喎？
上咩？
老師
問題啊，有冇
啊 database，但係我真係唔知自己個 database
係啊，我知 copy and paste OK。唔係啊，你咩嘢都唔做都 OK 噶，冇人理你嘅。
爆四哥今日都唔喺度啦，咪日都係。
查得住呢部嘢。夜市嘅，哇！我話落如果佢哋識講，會夾出。係啊。你要用翻一談到嘢，你要用翻230嘅知識嚟解釋。
308得唔得？
都得嘅，啲食量問題啦，係咪？
萬一但係萬一你釘嘅時候出啲差池嘅話，咁樣你到底真係唔買上去？但係我唔可以將我個釘冇成個拍成一個 video。咁呢個我可能好多萬一到時你出事你 blog 嘅時候或者有咩係我真係嚇死喎！用 database 嗰個 video 咪得咯。但係 database 嗰個一定要有個 software 嗰個30嗰個叻先得㗎嘛。喺嗰度跑。但係我嗰個明明就係自己個電腦先用嘅叻。
人家係人，喂真係睇清喎。
係啊，但係。
幾靚？有1分鐘。YouTube 嘅勁啲。停咗喺度。即係減低少少。咁幫喺呢個應該 App 度睇到。search 唔到可能。